In modern physics called photon-particle collisions. Sometimes you'll see this referred to as the Compton effect. And I'm just going to give you a very simple overview of what this involves. I'm also assuming that we've already talked about the wave-particle duality of light, and that you know what evidence supports the wave model of light, what evidence supports the particle model of light, and what evidence supports both theories. I also am supposing that we've already talked about the relationship between the energy and frequency of light using E equals hf, and that you have some understanding of the different models of the atom. So to start with, I'd just like to remind you that with the photoelectric effect, remember that's when we were talking about using visible light waves to strike a metal surface, and we called those incoming light waves photons. Those light waves, or photons, particles of light, strike a metal surface, and if they strike with enough energy, electrons will actually be ejected from the surface. And if they strike with enough energy, those electrons will not only be ejected, they will also leave with some kinetic energy. So today I want to talk about what happens when instead of using visible light, we use X-ray photons. Because X-ray photons, as you know from the spectrum in your reference table, you can see here on this slide, have a higher frequency than visible light. They're on what I consider to be the dangerous end of the spectrum. They're on the violet end of the spectrum. They overlap with gamma radiation and ultraviolet radiation. They have high frequency, high energy, low wavelength photons. X-ray photons, if they have a higher frequency, we know that they have to have a higher energy according to the relationship E equals hf. Remember, E is energy in joules. H is going to be Planck's constant. That never changes. That's on your reference table. And then F is the frequency in hertz. So because H is a constant, that means if I increase F, if I have a higher frequency, I have to have a higher energy. There is a direct relationship between energy and frequency. When X-rays strike a metal surface, not only are electrons ejected, but some electromagnetic radiation is also given off. That's what I really want us to focus on today. I want us to focus on that electromagnetic radiation that's given off. Because that electromagnetic radiation that's given off is a lower frequency radiation than the photon that hit the actual surface. So we have an incoming photon that strikes the metal surface, some electrons are ejected, and also some photons scatter, but the scattering photons, or the recoiled photons, actually recoil at a longer wavelength, lower frequency radiation. Why does that happen? So whenever a light ray, like an X-ray, strikes a metal surface, there is a collision between that photon, that light ray, and a particle that takes place. This is a great picture of what a scientist might see if they use a particle chamber. This is actually what it looks like when they see the collisions that take place. It's amazing that they can actually figure out what the heck is going on in there, but they're really looking at the collisions and what's bouncing off from what after the collisions have taken place. They're looking at the paths they take, the angles they hit at, and so forth. So when a photon and a particle collide, usually the particle is at rest. We're assuming that usually the particle is at rest. So the photon comes in with the speed of light, because all photons travel at the speed of light, 3 times 10 to the 8. That photon strikes that particle that's at rest, and during that collision, both energy and momentum are conserved, making this an elastic collision. If energy is conserved, that means that some of the original energy in the photon has to be transferred to the electrons that are ejected, and also to the electromagnetic radiation that's given off. That means that the energy of the emitted electron and the energy of the resulting recoil photon have to add up to equal the original energy of the photon. That's what conservation of energy is. The total energy of the system before the collision has to equal the total energy of the system after the collision. And the same is true for momentum. Before the collision, you have an incoming photon that's moving at 3 times 10 to the 8 meters per second. It has momentum. Now, just because a photon doesn't have mass doesn't mean it can't have momentum. It just means that its momentum and its energy are not related to mass because it doesn't have mass. Its energy and frequency, or excuse me, its energy and momentum are related to its frequency and its wavelength. And the original energy and momentum before the collision has to equal the energy and the momentum after the collision. So the energy of the electron that's moving away from the surface and the energy of the recoil photon have to add up to equal the original energy. So it makes sense that the new photon has to have less energy than the original photon because some of the energy was transferred to the electron. So what does a photon with less energy look like? According to E equals hf, according to that relationship between energy and frequency, if a new photon has less energy, it has to have a lower frequency. Remember, h is a constant and that doesn't change no matter what. So if it has less E, it has to have less F. They're directly proportional. Now, what does that mean for the photon's speed and wavelength? Because you can bet they're going to ask questions on this on the Regents exam, and they're going to try to trick you here. Because you know it's a photon, and we know all photons travel at the speed of light, 3 times 10 to the 8 meters per second. So the velocity of that recoil photon after the collision does not change. That photon is still traveling at 3 times 10 to the 8 meters per second, of course assuming that we're measuring the speed in a vacuum, that it's moving in a vacuum. Now, according to the relationship between velocity, frequency, and wavelength, v equals f lambda, if the velocity is a constant and the frequency gets smaller, the wavelength has to get bigger. We know that already. So here's a great picture of what the photon-particle collisions look like. And as I said, it's sometimes called the Compton effect for the scientists who worked on it. You can see in this diagram that you have an X-ray photon that's got a very high frequency and a short wavelength, and it's traveling at 3 times 10 to the 8 meters per second because it's a light wave, even though we can't see it. It strikes an electron that's at rest. And then you can see in the diagram that the electron is scattered at some angle. So now the electron gains speed, which means it gains energy and it gains momentum. That means the photon has to lose speed or lose energy or lose momentum. And we know a photon can't lose speed because it's a light wave. It travels at 3 times 10 to the 8 meters per second in a vacuum. So if it can't lose speed, it has to lose frequency. And you can see here that a much lower frequency wave is emitted with a much longer wavelength. And that is the Compton effect, or photon-particle collision in a nutshell. So remember, during a photon-particle collision, momentum and energy are both conserved. Thanks very much for watching.